educational problems themselves can be formatted as sequential problems in many different ways. Whether a particular concept makes sense after a set of concepts that this student has learned, right? What concept should be present to the student next so he best understands this previous concept, best understands this new concept based on what he knows previously, right? What question should we show him so that his learning is maximized based on the questions that he has solved and based on the questions he has failed previously, right? So lot of these kind of things can come into educational sector ka sequential modeling. And in general, there will be a lot of sequential modeling problems used there because a lot of educational sector deals with natural language, right? So you have questions and answers or question answering based on paragraphs, right? Verbal reading and then question answering, right? So those things can definitely be helped by sequential models like BERT or T5 models, right? So there's a lot of work in that area. What I think is, in my opinion, the future scope is there is a lack of data sets and standard measurement there, right? Like, for example, what question should I suggest to the student next so that his learning is maximized based on the previous questions that he has solved or learned, right? So that kind of model development, you need some standardized data sets also. So I think the lack of data sets is the biggest challenge in that sector rather than the lack of problems or scope. I think the biggest scope of deep learning and these ML technologies is in revolutionizing educational sector now because that sector is pretty much untouched, right? Not much has been done there, I feel. So you can work on building data sets as well as on solving other problems there, right? Yeah. What is the difference between Viterbi algorithm versus forward versus backward algorithm in context of hidden Markov models? Ashutosh, would you be able to take that?
Sure. So I think both of them are kind of used as the name suggests. It has some form of dynamic programming component for each of them. So in forward, backward, you're either. So I think Viterbi is generally used for inferencing or decoding. So in the specific case for HMM, when we were talking about pause tags, so what was happening was you've been given an observable state, which is the sentences that you already have been given. That's kind of your training set. And you've been given all these aspects or the parameters, for example, the emission probabilities, the transition probabilities, as well as the initial states. And then you need to come up with the algorithm which tells you exactly what is the inference part, which is just predicting the sequence of discrete states, or in these terms POS tags that you need to predict. You have to look at it carefully because here Viterbi algorithm, if you look at the formulation, it involves maximization of certain paths. So you need to make sure that once you're traversing through that algorithm, you're taking the maximum of those paths, and the dynamic programming component just takes or makes sure that there are like 5 optimal paths which can reach to the 6th path, and these 5 and 6 are basically time steps that I'm talking about. So then you need to see which is the path that is maximizing this, because in the end what you need is the highest probability or highest likelihood state transition vectors that you can obtain given the original sentence. In the forward-backward algorithm, it's a clever trick to apply for these likelihood calculations and so on. But there, if you see the formulation, the main goal is to have these alpha and betas. Alpha just carries the forward path and beta just carries the backward path. There's no specific maximization that you need to apply onto the different formulations. You take the sum over all the forward paths. The good thing about forward and backward algorithm again is it reduces the time step. It's a dynamic programming kind of algorithm where you just consider the previous time step and all these information, because of the Markovian property as well about the HMM, all these properties are stored in the previous time step. So it's a clever algorithm where you just need to figure out what is the forward and the backward path, combine them both, because that will be helpful in figuring out what is the likelihood of the sentence given the HMM or the final trained HMM model. So one thing is both of these are common terms that they use dynamic programming. They involve the use of these learned models, which is you need to know the emission, transition, as well as the initial probability. The difference just lies between the maximization component that occurs in the Viterbi algorithm, and there's no maximization implicit maximization that occurs in forward backward. So finally you'll do maximization, but it doesn't involve terms which have a DP component inside which we do maximization as well. So if you write it down, I think it'll make more sense. Probably that's also covered in the work as well. So if you look at the formulation, you'll see that there's a max inside a max in Viterbi, but it's a max of overall component in the forward backward algorithm. That's probably it. Preetham, do you have anything to add on to this?
No, I think that sums it up. Right. In general, I think forward backward algorithm is used for training the model, where we want to basically fetch the marginal probabilities, and Viterbi is used for inference, where we want to get the best, the most likely sequence. Yeah.
Sure. Okay. Next question is, please explain encoder and decoder pre-training. So I think this is in context of transformer models and in context of translation models from Badanov attention type of works. So in context of this Badanov attention and the translation works, right? The encoder and the decoder models have a very specific functionality, wherein the encoder is meant to encode the input sentence, which is coming, let's say, in one language into a single representation, and then the decoder will take that representation, attend to it, and then decode it in the translated language, right? So essentially you can think of encoder conceptually as something that encodes the input sentence into a particular representation, and then the decoder is trying to decode that into the next language that you want to translate it to, right? That is in context of this translation works, right? Now, in case of transformers, encoder and decoder pre-training is also very similar. Like in T5 models, you have an encoder and a decoder, but it may not be for translation. It could simply be for question answering type of tasks also, wherein your encoder will take in the context and the question, and your decoder will then use the representation from the encoder and then try to output the answers to the context and question that was fed into the encoder, right? So that's mostly how the encoder decoder is used. Now for the pre-training part, right? So in case of pre-training, what we do is for encoder pre-training, usually we simply take the output of the encoder and do a masked language modeling objective on top of it, which basically means that when I feed the sentence to the encoder, some words will be masked in the sentence that I feed into the encoder. The encoder's responsibility is to unmask those words in the sentence that I fed to it. And by unmasking, I mean it will predict those words which were masked. So if the sentence is the quick brown fox jumps over the lazy dog, I might mask the word fox. So the quick brown dash jumps over the lazy dog. Now the encoder has to predict that at that particular point, the quick brown dash, right? In that dash, there was a fox. That's the encoder pre-training. In the decoder pre-training, what we do is something little different. We simply ask the decoder to predict the next word. So the quick brown dash, fox, then again dash, jumps, right? So again dash, over, right? So it keeps going on and on, predicting the next word. That is the decoder pre-training. Attention models have a very good property, which is parallelization, which is why decoder training in attention models became really fast and parallelizable, and that was why one of the big reasons why attention models took off very well, right? Because decoder pre-training was parallelizable in attention models, while in LSTM it was a harder task to parallelize them. Okay. One thing I would like to address before about the resources. So resources like lecture videos will be shared, I think, post all the sessions are over, but slides you need to mail to mssummerschool@amazon.com to ask them if they can share the slides or not. Videos will be shared later on, so don't worry about the videos. Yeah. Okay, next question. When loading a model for downstream tasks, yeah, when loading a model for downstream tasks, what is initialized, and during the training, which weights are actually altered? Is it the encoder or the decoder? Right? Okay, so during loading a model for downstream tasks, what we do is, if let's say you have a T5 model, right, which has both an encoder and decoder, then we can actually do both, train the encoder and the decoder, right? So, for example, T5 for summarization, if I'm training, wherein the T5 model will take in the larger paragraph and provide a summary. In that case, I can train both the encoder and the decoder, right? If on the other hand you only have a GPT-2 model, which is a decoder only model, then you only train the decoder because the model itself is only having the decoder, right? So it is very much dependent on the type of model and the task that you have, and it is also dependent on the resources that you have. For example, you might decide to train only the decoder and only the last layer of the decoder if you have, let's say, a smaller GPU or a CPU only machine, right? So it's also dependent on the kind of compute resources you can use to train. That answers that. It was told that we leverage multi-head attention such that the dimensionality of output is same as the embedding. So is it mandatory to get the dimensions same? Also, I read that each head is capable of learning different linguistic features. How is it so? Okay, so from the dimensionality perspective, do we need the dimension of output same as the embedding? It is basically good to have, because then the architecture becomes simple. You have just repeatable layers, right? Whatever came in as embedding, if you output the same dimension, then your layers can be the same layers can be repeated multiple times. You would have different weights, but the code and other things for the layers will be same. So it becomes easy to analyze and also store them and deal with them later on, because of which we tend to keep the weights same, right? There is no benefit in changing not the weight, sorry, the dimensions. There is no benefit in changing the dimensions per se. There have been experiments where people have tried to change those dimensions by keeping the embedding dimensions small, making the remaining dimensions larger and all. Those experiments have usually shown that there is not much benefit in doing those kind of modifications. So for simplicity, this has been picked up. Keep all the dimensions the same, right? The other question about attention heads learning different linguistic features, it's kind of like model ensembling, right? So if your BERT model or GPT model has multiple attention heads, each attention head could focus on a different kind of linguistic feature or a different kind of detail to learn, right? And as a result, what happens is if you have more attention heads, then each of them could learn a little different linguistic feature. Again, this was shown in previous research works that some attention heads learned tasks like NER. There is a particular work in 2020, I think, which basically goes by like this, right? BERT reproduces traditional NER pipelines, right? So they prodded different attention heads and they found out that yes, BERT model actually, different attention heads are able to do NER and other NLP tasks, right? Which we were traditionally doing, right? So that is actually found out empirically, that these heads are able to do these things, and it makes sense because we used to earlier also accomplish natural language tasks by following these various algorithms. So it kind of is intuitive that a BERT model, which is learning from the data that we have provided, will try to learn similar algorithms that we figured out from the data ourselves earlier on to achieve those NLP tasks. Right. So given that the data we fed to the BERT is same data that we use ourselves for learning, so it is very much that BERT also tended to learn similar patterns and things and is able to accomplish similar tasks, right? BERT and any other language model that we use these days.
Right. One more thing that I'd like to add to this is we do not really constrain each head to do this task. It's just the consequence of the learning that each head is able to learn something. So it's the onus is upon the person who is doing the analysis to see what head is actually predicting what. So it was just discovered from this basically Bert uses or at least explains the classical or discovers the classical NLP pipeline is through the layers. As we're moving, we know that initial layers will kind of capture some sort of syntax, but later the semantics and all these come into picture, and then we'll look at these heads which we'll look at during the analysis, but we do not pose a specific constraint on the heads that this has to learn NER or this has to learn some pause tags. It's just the consequence that it arrives.
Yeah. Can you explain a bit more about multi-head attention versus attention layer? Multi-head attention and attention layer are like two different concepts altogether. It's basically a single attention layer has multiple heads. Like if you look at a single neuron, like a single neuron has multiple inputs, and every input has a different weight, right, given to it by the neuron, right? So similarly, you can think of an attention layer having multiple channels of inputs, which are its heads, right? But in this case, one head is not a single weight and a single input number, but rather one head is basically, let's say, 64 different weights and 64 different inputs, right, that go into that head. And similarly, multiple different heads take in these group of inputs in the same attention layer, right? And then these heads are finally combined using the softmax logic and the overall attention formula, right, to aggregate all the total attention scores and then pass on the information, right? But the overall gist is that the overall operation is an attention layer, while within that there are various heads, like how within a neuron there are various weights, or within a layer there are various neurons. In a similar fashion, within an attention layer there are various attention heads. Okay. How does fine tuning work? Does they change the weights of neural network? What exactly happens to the model during fine tuning? Okay, so fine tuning works by changing the weights, as you know that when we fine tune the model, we take a pre-trained model that already has some weights, we give it our own task data, and then we fine tune the weights of the model for our particular task, right? So fine tuning does change the weights, and to what degree it changes will depend on how you are doing fine tuning. If you are doing fine tuning with a very low learning rate, then the weight change may be lesser or the weight change may be higher. There are problems like forgetting that happen with fine tuning. If you fine tune too much, then your model will forget tasks that it was able to do before fine tuning, because fine tuning has changed the weight too much, right? And when it comes to what exactly happens to model during fine tuning, that's a active research area basically. Like for example, in large models, it has been found that fine tuning brings out already inherent abilities in them of able to do tasks, and it magnifies those abilities, right? In case of some large models, right? In case of GPT 3.5 and GPT 4 by OpenAI, they mention that fine tuning does not help the model to learn new facts. So do not use fine tuning to teach model new facts, right? In their own fine tuning recommendation, they give it. So what happens during fine tuning is very different for every model. For smaller models, the weights simply change a lot, and then your model gets very tuned to how the task that you fine tune it for is, right? In case of larger models, the fine tuning result is a little different. The model still has capability of doing older things, but it also gets a little more tuned to doing what the new thing you are trying to teach it to do. Can you shed some light into sentence transformer? Do they form a more robust architecture? No, so sentence transformers do not form a more robust architecture. They're based on transformers only. Sentence transformer as a library is a Python library. It has a little different purpose from general transformers, right? You can think of general transformers as a generic library that you can use transformers for anything, for vision, for other things as well, right? Sentence transformer is specifically meant to encode a single sentence into a vector representation, or provide the score between two sentences, whether the two sentences are aligned or not. Natural alignment questions, right? Like I dropped a ball, the ball bounced back, right? That's the two sentences are aligned, right? I dropped a glass, the glass bounced back. The two sentences are not aligned because the glass will break, it will not bounce back, right? So sentence transformers are meant for these two tasks: either provide a sentence embedding or provide a score between the alignment of two sentences. They have specifically trained for that, they have data sets for that, they have specific models which are optimized for that, but it's very specific to that. So if you're working in information retrieval or search, those kind of domains, then sentence transformers is very useful for you, but they're not a generic transformer library, they're a very specific use case.
Also, just to add, we typically use the embedding in the CLS token present in BERT as the sentence vector, CLS vector, or take the mean of all the output embeddings, etc. But there are also some specific techniques to tune those vectors using a Siamese architecture kind of framework. So let's say you have a data set containing two classes. So let's say you have 1,000 samples belonging to one class and 1,000 samples belonging to some other class. One way to generate to use the Siamese network is to try to bring all the sentences belonging to one class together and sentences belonging to other class away from each other, opposite classes away from each other. So there are some ways to use Siamese network. I think one of the data sets that is typically used is NLI data set, where you have whether one sentence is inferring or contradicting other sentence. So there are small differences, but at the end, in terms of use case, whether it will provide a lot of value or not.
BERT model versus T5 model. I will kind of give you a little bit of contrast there, which will help you get an idea why T5 is needed even, right, if we have BERT. BERT model cannot give you something like contextual question answering. So if I have a paragraph and I have a question and I want that question to be answered from that paragraph with one or two long sentences, right? Then BERT model cannot do that, because BERT model can only either give you a representation of a sentence, like how Preetham told you, based on the CLS token, or BERT model can give you masked words infilling, right? So if you have masked a word, it can fill that word in, but it cannot generate language out of complete free-flowing language, right? So what you do is you use a model like T5, which has a encoder which will take in the context and the question, right? And after taking in the context and the question, the decoder from the T5 will take in the representation which comes out of the encoder of the context and the question. The decoder will generate the answer, right? So the decoder can generate free-flowing answer. So every use case where you have this kind of stuff, you can actually get a lot of benefit from it. Lot of places, even the T5 actual paper showed that you can do things like translation using T5 like models, right? And you can even ask it simpler questions where you have a yes no answer, but the yes no answer will come from the decoder, right? So anything that BERT can do, T5 can also do, but it can also do more things like translation or making a summary of a larger input, right? It can do those things as well. So it only expands the abilities, The main challenge is that since you have an additional decoder, so you have to spend extra compute on running that decoder. So in places where BERT makes sense, we tend to just go with BERT rather than using a T5. Okay. While implementing these techniques on a project, we have to mathematically find the best approach, or we can do it by just that particular models. I am not sure if it is about hidden Markov model or it is about transformer, but the general advice in case of whether to mathematically find the best approach versus take particular models would be key. Go for a good amount of literature survey on the domain that you are trying to solve, right? And in that literature survey, you will obviously get a good amount of hints on what works and what does not work for that particular domain, right? And based on your literature survey, you might see that some particular models or some particular approaches work well. You will make those as your baseline while developing further. And if you are doing research, then you might go beyond the baseline. If you are working in the industry and you need to productionize something really fast, then you might just use whatever is in the literature already rather than trying to create new stuff out of it, right? So mostly do a lot of literature survey and find out for your domain what has been done and then follow up from there. How GPT generative pre-trained transformer model works in ChatGPT. Okay, so ChatGPT is an interesting question because it's not just GPT that makes it work, right? It's not just the model architecture that makes ChatGPT work. There's a lot more that has gone into making ChatGPT like systems work, right? So the first thing is obviously GPT, which is a decoder only model. So in a decoder only model, you can generate free flowing language, right? You can basically give some preamble text like write me a story or write me a poem, right? And then you can ask it to generate text, and it will keep generating text one by one by decoding at each step, right? So at each step, it will decode one word, then feed it into itself, then decode the next word, feed it into itself, and keep repeating that, right? So that's how your decoder model works. Now, in case of ChatGPT, the big breakthrough that came from ChatGPT models was not this encoder, decoder, or decoder decoding, but rather how they trained it, right? So they trained it for way longer than other models do, right? They have a lot of long training that they did. B, they also did something called as RLHF, that is reinforcement learning from human feedback. So because of that human feedback component, ChatGPT is working very well compared to previous models. And three, the model is itself very large. So what we have seen in transformers case, especially in decoder models, is that the larger the model, the better it works. So there is obviously you want smaller models to help you run them, but if you keep increasing the size, the model keeps getting better. Right? We are only limited by our current hardware in the sense that we are not able to make bigger models because our current hardware is limited. But otherwise, if you keep making bigger and bigger and bigger models, they will keep improving. Okay, you don't have to do anything else. You can just keep making them bigger. It will still keep improving. So they did all these things. That's why ChatGPT works really well. And similar systems like Claude's, Anthropic's Claude, or other systems also, like Amazon has Bedrock that also provides you access to Claude, right? So those systems work very well because of these certain techniques I talked about. Can you suggest efficient algorithms in low-end devices for face recognition? Low-end devices, I would go for YOLO V5 or something similar, but I'm not very sure about face recognition based models. So I would advise for literature survey rather than taking my word for it. And from a library perspective, you would have to check if the particular model is implemented in some library like Onyx, ONNX, Onyx, that is a inference library, or TF Lite, that is another inference library, or any other common inference library that is for low resource inference, right? TensorFlow Lite and Onyx are two that I know of. There is one Apache TVM also that I know of, right? So these libraries, if the model is implemented in one of those libraries, then you will be able to use them much easily rather than porting them yourself. Can you tell how decoder only, encoder decoder models are fine-tuned differently? I think I talked about this earlier, how encoder only, and encoder decoder models are fine-tuned differently. To summarize what I've already talked about, encoder models, you train them by doing masked language modeling, right? So you have a sentence, you mask some words from the sentence, and you ask the encoder model to predict that masked word. Decoder model, you ask it to predict the next word. Encoder decoder models, you generally pre-train them for question answering, or you pre-train them for summarization, right? So pre-train or fine-tune, right? You can fine-tune for the similar task, right? So that's how mostly training is done. For encoder only models, for fine-tuning stage, you usually only fine-tune the CLS token ka thing, like you fine-tune for sentiment classification, let's say. So you will have a sentence which has positive or negative sentiments, and then you will use the CLS token, put a linear layer on top of it, and then use a classification header, right? And that will constitute your backpropagation signal for the encoder only model. In case you are only doing fine tuning and you don't want to do this masked language modeling, right? Because you just want to predict the sentiment, then you will just use the CLS token representations. Even though encoder decoder models are primarily used in NLP with attention mechanism, I have used them as encoder, decoder, CNN, RNN model in different occasions. However, both do not have encoder attention mechanisms. Is there any valuable benefit that could be obtained from attention in such CNN, RNN models too? So, as I talked about, encoder decoder is general paradigm wherein you can have an encoder made of attention, or you can have an encoder made of LSTM or CNN, right? So similar. And if you are talking about encoder decoder in CNN based models, I think you are talking about something like a unit architecture, right? Where you are trying to do semantic segmentation or some other task like that in image domain, and you have a unit like architecture. Attention can help even in those areas, because attention as a general mechanism has been shown to improve performance in various models without any additional things, right? Like you don't have to do anything else. You just add attention blocks and you can get additional performance. So it does help in improving performance. There are recent CNN models which actually incorporate both attention and CNN paradigms into them for improving their performances as well. How does Alexa currently perform intent and NER tasks? I'm not from Alexa, so I would not give an answer to that question. Sorry, my Alexa.
Yeah, maybe I can just describe briefly. So, in general, like several other systems, not just Alexa, but several real-world systems, we use transformer models to basically understand what's the intent behind what the user is saying. So, for example, if the user wants to set up an alarm, that's a different intent compared to when the user asks to play some music. So we try to understand the user intent using a classification model that is based on transformers. So there are several other systems as well, but broadly they are based on transformer architecture.
Sure. How sequential model avoid plagiarism? It is dependent on two things. To avoid plagiarism, you can do two or three things, right? So, first is just don't put plagiarized content in your training data. So, if you don't put plagiarized content in your training data, your model will not plagiarize because it has not seen that data itself. So, that is the first thing that you can do. In case your training data is contaminated with plagiarized content, like you have mistakenly put books and stuff like that, what you can do is during inference you can filter some utterance out, right? Like let's say if your model is putting direct quotes from Harry Potter, right? Harry Potter the book, right? So you can kind of do substring matching and filter those things out, right? That is the second way. The third way, which usually Bing uses, right? Bing Chat uses, is it uses the sources, but then it also references them, tells you that these are the sources it used. Hence, it's actually not plagiarizing, but rather it is saying that I'm referencing those works and you can go and visit the link. So all these three things you can do to avoid plagiarism in sequential models. Can you please elaborate on channel and spatial attention? Is this for vision transformers? Hey, do you guys know what this means? Elaborate on channel and spatial attention.
Yeah, I think it's basically on vision transformers itself, any kind of CNN mechanism. So probably these things, images are captured in different RGB channels. So through the global features, I think channel attention just captures the global features that are present in the image, while spatial attention captures any locally present spatial features inside the images. So in terms of if you're looking at it from the perspective of images, that is kind of the main difference that I know of. And if you want to understand it from the sequential perspective, then I think a good thing to be referred to for this is something like long formers, where they have localized attention for some part, but at the same time they're capturing global attention. So I think that is the direct analogy for channel and spatial attention as compared to sequential models. But I think do they have like lectures on vision or CNN sector?
They do have a CNN session, but in the CNN session, vision transformer is not covered.
Okay. But I think it'll be a better question, or has it already been covered? That also I'm not sure of if it's already
that session has been already covered.
Okay. Then I think this is like the key difference. So you just have to look at channel attention as global feature or global attention capturing, which figures out, for example, what is the scenery about, let's say, and spatial features are what are the elements present in the scenery. That's what you can kind of figure it out from there. Yeah.
How is neural network different from HMM while understanding the text? Okay, this neural network, in the sense that transformer or LSTM, in case of hidden Markov model, if you notice, right, the probabilities are based on just the last token, right? So you have transition probability, you have emission probability, but they are all based on the current state only, right? What state you are in, based on that you will have some transition probability to the next states where you can go, and you will have some emission probability of what word could be emitted, right? But the problem with that is that yours next state and what you emit is entirely dependent on just the current state, right? But in case of neural network, right, it can be dependent on the entire context, right? Like if I write the quick brown fox jumps over the, right? So after the, you have lazy and dog, right? But in case a hidden Markov model takes this sentence, it will only see the, so it will fill the word after the, whatever most probable word it thinks after the, right? The quick brown fox jumps over the dash, right? So it will fill in the word after the, whatever it thinks is most probable after the itself, not after the entire sentence. While in case of neural network, especially in case of RNN, LSTM and transformers, they can look at the whole sentence and then fill in the word that is most probable after the entire input sentence that we gave them, right? Not after just the current word. That's the major difference. Both are modeling the probability of the sequence, but HMM is modeling the probability of the sequence by only looking at the last step and trying to say what will be the probability now given just the last word. On the other hand, transformers can look much beyond that and give the probability of what will be the next word. Right. General approach towards NLP tasks is research, or are there some thumb rules? Especially pre-processing for transformer tasks can potentially remove context from the data. I would say that it largely depends on the problem statement that you're solving. There are obviously some thumb rules, like for example, if you have multilingual data, then you would benefit from using a multilingual model, right? If you have Hindi and English mixed data, like English data, then it is better for you to take a model which is trained on English data rather than taking simple BERT, right? If you have data which has a lot of spelling mistakes, then try to correct the spelling mistakes through a different model and then feed it to your actual model which is trying to do something, right? So there are certain thumb rules, like you can clean your data a little bit, you can uh, convert your data to a better format, right? Those are kind of thumb rules that you can use, but usually I would say is that go with what your current domain existing works do, and then try to see what results you are getting, and based on the results you will try to see which examples your data is not working, right? And in the examples that your data is not working, you can then try to create data for making that situation work, or you can change your model, you can do something else, right? So it's mostly working backward from what you want to get. That's the usual approach that NLP tasks take these days. Can you tell how the decoder model predicts the next token and size of the output token? What is differ regardless of the input token length, word length? The size of the output and how the decoder predicts the next token, right? So, in case of hidden Markov model, let's say, right, you have a emission probability, right? What will be emitted, right? In the similar sense, in case of transformers also, given a set of input words, the next word will have a some kind of representation, right, from the last layer of the decoder. That representation will be passed into the softmax and into the word embedding layer, and then into the softmax, which will give you a probability distribution over all the words, right? Once you have that probability distribution over all the words, you can then sample from that probability distribution a more likely word versus a less likely words. Similar to how you would have sampled from the HMM also based on the emission probabilities, you would sample from here also. Here the decoder is giving you the probability of what could come. There the HMM emission probabilities were giving you that, right? But once you sample from that one word, let's say some word comes out, right? Then you feed that word again along with the previous sequence into the decoder again, and then you get the next word, right? So you keep getting words like this. Then you would have specified your model either one of the things, like generate only 100 words, right? So what will happen is key in your program, in your for loop, let's say you would have key up to 100 only I will generate, and then I will stop, right? So if you are using some library like Hugging Face transformers, they already have this as a parameter where you will specify max tokens and it will generate that many number of tokens only. Okay. Or you would have specified a stop sequence. So you will say stop once the word stop is generated, right? So you will tell it once the word stop is generated, you stop, or once the word full stop is generated, you stop, right? So then the library internally takes care and checks if a full stop is generated, then I will stop the loop, right? But the overall logic is that it happens in a loop. You can run the loop for a fixed number of times which you specify, or you can run the loop till the stopping criterion you have passed matches, right? That's why it can generate variable length, because if you are not providing any length, then whatever the library has configured will keep generating, right? Internally, whatever the library has configured. Comparison between architectures of MedPalm and GPT. Do not understand the pathway system in Palm at all. From what I understand in case of Palm model is the pathways system is a little bit like a, what do you say, it's a good wording of it, but overall it's just a mixture of experts model mostly, wherein they have an ensemble of multiple models at each layers, multiple at each layer they have an ensemble, and then overall the final ensemble is the word that is the model that gives you the result, right? So what happens is you have this ensemble type of model where if you look at works like switch transformer or mixture of experts like works, you will be able to better understand how the palm system overall works, right? GPT, we already discussed about it, so I'm not going to go into that. Okay, I think we are mostly out of time. So there was one question very early on. Can we talk about our journey into Amazon? Let me just check that question first. What do you guys remember? Yeah, I'm not able to find that question. So
Yeah, this is towards the end, if possible, for all mentors to talk about their journey to Amazon.
Yeah, Preetham, would you like to share your journey?
Yeah, sure. So, yeah, as I mentioned, I joined 4.5 years ago. So, like, I have been working in Alexa since the beginning. Yeah, my journey has been great in terms of the learnings. So, we were the first Alexa team in India. So, there were a lot of things in terms of launching new models for Indian Alexa users and launching new languages. We launched Hindi. So yeah, it has been great. And in terms of the team culture, I would say learning is one thing that is prioritized a lot. Learning and collaboration. So we collaborate a lot with teams, Alexa teams from other locales, and yeah, that helps in in learning better.
Awesome. Ashutosh, you want to share?
Sure. So mine was a slightly different path. So I did my PhD in NLP, and during that time, I interned with Amazon twice. So these were with different teams. One was focused on general core machine learning ideology, and then the second one was an NLP based, which was a team with AWS AI. So these were the two main teams that I worked or interned with before joining Amazon as full-time in the search wing. So for us, like the collaboration happens, as you know, like we have, I mean, all these Amazon application have a search tab, and then we have to collaborate across a lot of different modalities in terms of Prime Video or Amazon.com search and so on. And we also need to make sure that whatever products that are being delivered, those catalog teams are also kept in mind while we're working with understanding those texts or understanding the queries that users issue and display the resultant products to them. So that's kind of has been my journey. It has been slightly longer in terms of PhD, but at Amazon as a full time, I've just been here for 1 year. I think Faizan has been here for more than both of us combined, so I think he'll be a bit better.
Sure. So I came to Amazon in 2017 actually. Before that, I was in Flipkart for 2 years. So I passed out from my college, then joined Flipkart as an engineer mostly. Then from Flipkart to Amazon also as an engineering person. Then in Amazon, I shifted to ML as an opportunity within the seller fulfillment org. And then last 1 year, I am in the core machine learning team. So mostly my journey has been a lot of it is on the Amazon's initiatives like ML Gurukul and all, where they actually train their internal talent for shifting into machine learning, right? So that helped a lot, wherein we internally have programs to nurture talent into ML, even if they are coming from engineering background, right? So I did not have any ML specific education in my engineering. I came from simple electrical engineering background only. But then internal Amazon programs, ML Summer School, like programs, we also have internally ML Gurukul and other programs. that helped a lot in getting me to transition into a machine learning role, right? So yeah, that's mostly the journey that I had. Been pretty fun actually, given that you get a lot of time to do research, read, and also keep up with state of the art stuff. So it's pretty nice to see all these things changing so fast and so uh, much stuff happening, right? So yeah. So yeah, we are out of time right now, so we would have to take your leave. Thanks a lot, guys, for joining in. And it's a Sunday, so I think you are studying. We are also helping you out. So keep hustling, guys, and all the best. Thanks, guys.